All right, this is physics lesson 4.2. Here we go. So we already know what a force is. Newton's laws tell us how forces affect the motion of an object. So let's learn the first law. Newton's first law, also sometimes called the law of inertia, says an object at rest will stay at rest, and an object in motion will stay in motion unless acted on by a net force, sometimes said as an outside force. Okay? You guys have seen this all the time. If you're presumably sitting at your desk, your computer is sitting there, and it's at rest. Your computer is going to stay at rest unless you push it. Okay? And then once it's moving, it's going to keep moving unless you then put another force on it to stop it. Okay? And keep in mind that there are different types of forces. Gravity is a force on it, so when you drop an object, that's the force that puts an object in motion. Friction works against motion, right? Usually. So there's all different kinds of forces, and these forces, according to Newton's first law, attempt to change the motion of an object. Okay? So here's how I usually write Newton's first law. What I tend to find is that this version of Newton's first law is great conceptually. An object at rest stays at rest, an object in motion stays in motion, unless there's a force on it. But it doesn't help you that much in terms of problem solving. So here's how I like to write it. I'm going to write these three statements on the board here. If one of them is true, they're all true. So it's all or nothing. If one is true, they're all true. If one is false, they're all false. All right, so here's the three statements. If the net force on an object, the first statement is the net force on an object is 0. Net force is 0. The second statement is the acceleration is 0. So if your net force is 0, that means your acceleration is 0. And this last one, you know, if the acceleration is 0, then the velocity is constant, but not necessarily 0. So the velocity is going to be some constant number. Okay? There you go. So Newton's first law says those three statements are equivalent. There it is. Write it down in giant letters somewhere in your notes because you're going to see it all over the place this chapter. Newton's first law says these three statements are equivalent. If the net force is 0, then the acceleration is 0, and the velocity is constant. Or, conversely, if the net force is not 0, then the acceleration is not 0, which means the velocity is going to be changing, right? This is saying that if you cause a net force on an object, you're going to change the velocity. Okay? So what this means is that, in general, you need a force to change the velocity of an object. You need a force to get an object moving or to speed it up, but not to keep it moving. You need a force to stop an object or to slow it down, but not to keep it moving. You need a force to make an object turn, but not to keep it going straight. All right? So please don't make the mistake of thinking that if an object is moving, there has to be a force on it. It's possible for an object to move at a constant velocity, even if there are no forces on it. And we're going to see that as we walk through a couple examples here. Okay? So let's start here with example 4. Why is this example 4? I feel like this is example 1. Whatever, it's an example, and it's about a bowling ball. So I'd like you to imagine a little kid pushing a heavy bowling ball. I'm picturing like a 4-year-old or something. All right, little kid that's just barely strong enough to even lift the ball. All right, and he's going to set the bowling ball down at the the start of a bowling lane, and he's going to push it down the lane. Okay. So to keep things simple, we're going to assume there's no friction. We're actually going to learn about friction in a couple days. So for now, all of our examples are going to be frictionless unless it says otherwise. All right, so we're going to explore this example in a little bit more detail. All right, so the first thing that happens is the kid sets the ball at rest on the floor. All right, once he sets it down, there's no forces on the ball. It's just sitting there, right? And as a result, there's no forces. That means that your net force is going to be 0. That means the ball is not going to accelerate, and the velocity is going to stay constant, right? In this case, it happens that the velocity is 0 meters a second because the ball is not moving, right? So there's our three statements. That ball is not going to move unless somebody pushes it. Okay? There's a little asterisk here too that's probably worth commenting on. Technically, there are two forces on the ball. Gravity's pulling it down and the floor is holding it up. We're going to talk about those forces more later on. For now, we're just going to worry about the forces that might affect the motion of the ball, which would mean, left or right forces. Okay? So there it is. That's Newton's first law in action. The net force is 0. The ball's just sitting there. It's not accelerating. The velocity is not changing. It's just staying 0 meters a second. Okay? Now, then the kid's going to push the ball, right? So this step here, this portion of the ball's motion only lasts for a split second. We're talking here about the brief time interval while the kid's hands are physically in contact with the ball. All right, so the kid's going to push the ball. So here's the force of the kid. All right, there's no other forces on it, right? So in this one, the net force is whatever the force of the kid is. Let's say, I don't know, whatever. Maybe he pushes it with 20 newtons, whatever. I made that number up. Okay, so that means that our net force is going to be 20 newtons, right? So that means that because our net force is not zero, it means our acceleration is not zero, and the velocity is going to change, right? So the velocity is going to change from zero until from zero up to, you know, whatever, however fast the kid pushes the ball at. All right. If you're having a tough time visualizing this, let's do this. Here's a YouTube video. The quality on this is going to be sketchy because you guys are going to be watching a video of a video, but it'll help you see what's going on here. All right. So we got this little kid. He sets the ball down. The ball's at rest. That's part one. It's not moving until force. He kicks the ball. All right. So that portion there, we're talking about. There's a force on the ball just while his foot is in contact with the ball, right? So the force is from there to there, right? Just that split second while his foot is in contact with the ball, okay? The velocity of the ball changes, right? The velocity goes from, right now the velocity is 0, and the velocity changes to now whatever that is, okay? So that's portion 2. All right. So let's suppose that the velocity changes. We need to pick a number here so that we have a discussion point. So let's say that the velocity changes until it reaches, oops, that's supposed to say reaches, and I'm going to make up a number here, say 2 meters per second, which is probably faster than the ball is really going. But let's suppose that the ball is moving at 2 meters a second when it leaves the kid's foot. Okay? So now, let's move on to our next slide. Now the ball's going to roll down the lane, right? It left his foot. The kid pushed the ball with his foot in this case. The ball's going to keep rolling, right? But since the kid is no longer pushing it, there's no forces on the ball. The kid is no longer pushing the ball. That's huge. That means that the net force on the ball is 0, right? There's nothing pushing the ball forwards or backwards or anything, right? So that means that the ball's not going to accelerate, which means that the velocity is constant at however fast the ball was moving when it left his foot, which we said was 2 meters per second, right? So what's going to happen is the ball is going to just keep rolling this way at 2 meters a second because there's no force to cause it to speed up or slow down, okay? Again, if you need a visual on it, here's another little video. All right, different kid. Same idea. So here she is. I don't know who this is. Some kid from YouTube. She throws the ball. Hey, yeah, here's the force. Now the ball is moving. And now, after she pushes it, the velocity stays constant. Look, the ball's not speeding up or slowing down at all. It's just rolling because there's nothing to stop it. Okay? And it's going to keep rolling forward until it encounters an outside force like hitting the bowling pins, right? Okay, so there we go. All right, so step 3, once again, we've got a net force of 0. The velocity is constant. Okay, notice if you look at this drawing and this drawing, they're the same, right? In both cases, the net force is 0. The only difference is, in this example, the first one, the velocity was constant at 0. And in this one, the velocity is constant at 2 meters per second. Okay? All right, and then the last part of this would be the ball hitting the pins, right? So eventually, the ball is going to roll long enough that it will hit. Whoa, that is the worst bowling pin ever. Okay, so the ball is going to hit the pin, and as a result, there's a force from the pin. And so once again, our net force is not going to be 0 anymore, right? In fact, it's going to be negative something, which is going to mean that our acceleration is not 0. In fact, the acceleration is negative, which means the velocity changes, right? That's going to slow the ball down, right? Okay? That's probably not enough force to completely stop the ball. And so the ball will keep moving until it hits the wall, which will then exert enough force to stop the ball. Okay? I probably should have put in my velocity. What was the velocity? 2 meters a second, right? Okay? Cool. So let's see if we can summarize all this. So what I want you to do, I've got kind of a blank slate here. What I want you to do is imagine just a box sitting on a floor. All right? So if the box is just sitting on the floor, then, since there's no forces on it, your net force is going to be 0, your acceleration is going to be 0, and your velocity is going to be constant at 0 meters per second, right? Okay, so that's not rocket science. It's a box sitting there. Object at rest stays at rest. Okay, now, what happens when you push the box? So let's suppose we've got a box here, and Roy comes along and pushes it with, I don't know, whatever, I'm going to make up some numbers here, 10 newtons. So now what's happening is our net force is 10 newtons, right? So when I ask people what's going to happen, people always say the box moves. Yes, the box will move, but it's more important than that. The box will accelerate. In this case, that means speed up, right? As long as Roy keeps pushing. Okay, so what that means is, as time goes on, the velocity is going to increase. So if the box started at rest, as long as Roy keeps pushing it, the velocity is going to get faster and faster and faster. So the velocity is going to go, whatever, 1 meter a second, 2 meters a second, 3 meters a second, 4, 5, and it's going to go faster and faster. Okay? Now, remember, if we assume that this is a frictionless surface, then after he lets go of it, so let's suppose that it was moving at, what did we say in that last slide? 5 meters a second, I think. 5 meters a second, right? So if we assume that the box is sliding at 5 meters a second, and Roy stops pushing, then we're going to have a net force of 0, an acceleration of 0, and the velocity will stay constant. That says constant. At 5 meters a second, right? Okay, but what about this? Let's suppose that Roy had pushed the box with his 10 newtons so that it got to a velocity of 5 meters a second. And at that exact instant, Sally comes along and says, I don't want that box to be moving. So she pushes this way with 10 newtons. What's the box going to do? All right, and the common misconception that people have is people think, oh, well, those forces cancel out, so it doesn't move. But that's not right. Because look, you guys, what's the net force going to be? You got 10 newtons forwards, 10 newtons backwards, so our net force is going to be 0. Which, according to Newton's first law, means it's not going to accelerate and the velocity is going to be constant. The two drawings on this board are exactly the same right now. All right. The only difference is that in the second example over here, Roy and Sally are both pushing it, but since their forces are equal and in opposite directions, they cancel each other out. So it's the same as if nobody was there at all. All right. So now the question becomes, if Sally really does want to stop it, what does she have to do? Well, let's think about it. Roy, by pushing it forwards, was trying to make it go faster, right? Remember back here? When Roy was pushing it, the box went faster, right? So Roy's trying to make it go faster. Sally, by pushing the other way, is trying to make it go slower. So what's happening is Roy's trying to make it go faster, Sally's trying to make it go slower. Neither one wins, so the velocity stays constant. To stop the box, Sally would need more force than Roy. If Sally exerted, say, -11 newtons, then you'd have a negative net force, and that would cause the box to slow down and perhaps eventually stop if it slowed down for long enough to make it stop. Okay? So in other words, if your net force is negative, that's going to cause the object to, in this case, slow down. Okay? So please, 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 when you see a drawing like this, I'm going to circle it now, when you see a drawing like this, please don't assume that the object is not moving. All that we know is that the forces cancel out, the acceleration is 0, so the velocity is constant. All right, I'm going to stop there at 16 minutes. So I apologize for going over.